Hey everybody, Stoner Dave here, and today we're going to educate John a little bit about vectors and tension and the moment of inertia. Probably not going to get too much into that, but I do want to talk a little bit about the state of equilibrium. So I have here a little bit of stuff that I've pulled out of a physics book. I'm going to show this to you really quickly here, and I'm going to run through and actually show you the math that goes into this, right? So the biggest thing that we need to understand, angular momentum is very similar to linear momentum, and it's conserved. We can prove this by actually taking a look at all the forces that are involved, the rotation that's going into the system, and more importantly, the velocities involved. Now, a big caveat to the conservation of angular momentum is that we have to be dealing with a system that is in equilibrium. That is, there are no external forces or torques being applied to the system. Now, John's paper, he calls for a mass of 1 gram. I was not able to find something that I could tether to anything weighing at 1 gram that would be able to handle this kind of experiment, you know? Some of them were to the point where this velocity this initial angular velocity, a lot of these materials, it's just 1 gram. It's too light. You can't ignore the air friction at that point, the wind resistance, the drag. So the system that I have, I am ignoring air resistance 100%. We're not even looking at it, right? We're only dealing with forces of nature, the tension, gravity. Now, John does bring up a decent point, but it's irrelevant to this case, and that is that the force of gravity is rather small, you know? That's fine. It doesn't matter how big it is. The fact of the matter is that we know what it is. And because we know what it is, and we have the means to calculate the others, we can get a total amount of tension that's in that line. Because if we look at just the two-dimensional object, we could see that it's going around in this circle, but the tension that's making it go around in that circle is only responsible for the velocity that's going on in that circle. How far up or down it is from wherever we decide is the y-axis, that is going to be dependent upon that force of gravity. And that is going to be a vector or a portion of the tension that's going into the total tension. So let's take a look at what our physics books has to say about it. One second. Putting this away. I'm not done with it by far. Make sure it's out. I don't want to be burning weed in my pocket. That's the way. All right. So be mindful. I'm going to grab the camera here and spin it around, point it at what I'm looking at. So, all right. So this is a model of our system, right? We have this tension right here that's pulling this ball right here that has some velocity right here. It's going around here. Now we're told that it's angular, it's 2 revolutions per second or 120 revolutions per minute. 1 revolution per second equals 3.14 meters per second. So 1 revolution per second, 3.14 meters per second. This is pretty cool too. So 1 meter per second equals 2.37, which means that we're looking at about 14 miles per hour. It's a significant amount of speed going on there, right? And that's just our initial conditions. We're not even talking about when we reduce the radius. This is the reason why when you get down there, you can't do it. So in my physics textbooks, I found a formula for this tension. It's mass times the velocity squared divided by the radius. So if m 0.004 grams, so I put 0.004 grams, our velocity is 2 times 3.14, so we'll just go ahead and call it 2 pi times 2 RPS. And I'm making sure to note that this is seconds. You know, that this is a velocity, right? I know it doesn't seem like much when you're swinging that ball over your head, but that ball's going around 3.14159, blah, 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 blah meters every second. That's 14.06 miles per hour. Think about that. That's not a casual walk. You know, that's a brisk run at the least. I don't know too many people that can actually run this fast for any amount of time, you know. If you are, I'd love to hear about you. I know there are like some athletes out there, right? And this is squared, right? So that's all squared divided by our radius, which is 1 meter. All right. Now, this all being so many numbers, I did bring a handy dandy little calculator with us. So let's see what we have here. So I'm put parentheses up over the numerator. So what I'm putting in the calculator is going to look like this. All right. 0.004 meters times 2 pi times 2 revolutions per second squared. Close that parentheses, and we're going to divide that by 1 meter. Enter. 631.65 blah 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 times 10 to the negative 3. So this equals, it's 0.631. And that's newtons. 2.2 newtons equals a pound. So we're looking at approximately quarter pound. And we'll see why that's significant in just a moment. Okay. So this is we're just calculating the tension. This is the X component of tension. Now, as you can see from this line-up right here, this right here is the hypotenuse. This right here is typically what we would consider angle. Right here, we're actually considering this, the hypotenuse, right here, and this would be the angle. It's the same thing, you see. But what we're looking at right now is that this X value, as you can see from here, is equal to, well, let's see, if this was 0, what would the Y value would have to be some number, but at 0 degrees, the sine would be 0. Usually Y is sine, but in this case, the X is sine. The X component, right? Because if the value is 0 degrees, it still has to be something. It has to be something, right? So, no, if it's 0 degrees, I guess that would make it cosine. The cosine of theta. And that equals or no, it's t times cosine of theta. I'm sorry, I keep forgetting to write things down here, and I should have been better prepared. It's my fault. I've been smoking weed. So the x value, so tx equals t total, put a little tote right there, times the cosine of theta. We don't know what theta is, right? And we're going to go ahead and call this theta on the inside. It's not this theta. It's theta on the inside. You'll understand, because if you took trigonometry, you would have heard SOHCAHTOA. So the sine is the opposite over the adjacent, over the hypotenuse. Opposite over hypotenuse. Cosine is adjacent over hypotenuse. So this one over here. So as you can see, when cosine is 0, everything's in the x direction, nothing's in the y direction. So we know that it'll never be 0. Theta will never be 0 because there's always this force in the y direction. But this is kind of important, because right now we only have the x direction, and if the y direction is significantly small, we could just call this the total amount of tension. But we don't know, right? And how much of this, what this angle is we're going to find out is widely dependent upon this velocity, which is dependent on the tension. So this is fun stuff. So what we know is that this equals, and we're just going to approximate it to the 0.631 on paper, right? Now, Ty equals mg, and it also equals T times the sine of theta. Right? Now you can see how it's starting to pull itself together, right? So what is this equal to? Well, we know that the mass is 0.004, and we know the acceleration due to gravity is 9.8 meters per second squared, right? There's grams, meters per second squared. Oh, that gives us a value of newtons, right? So let's go ahead and pull up our handy dandy calculator here, and I could do this one in my head. It's like 36 plus point, so like 0.0392, I'm guessing. But let's do it on the calculator. So 0.004 times 9.8. You can see it's 39.2 times 10 to the negative 3. 10 to the negative 3 means we move this over 3 places. Equals 0.0392 newtons. And that is a very small number, right? So from here, what we're missing is this theta, right? And they're both the same theta. But what we know here is opposite over adjacent. So if we do sine over cosine, right? We should get sine. We should get theta. Inverse y over x. All right, so here comes our moment of truth. So I have to hit the second button here, and the tangent function will give us a tan inverse. Now we can just plug in these numbers, right? 0.631 divided by 0.0392. Oops, I did them backwards. I'm so sorry. It's second tan inverse 0.0392 divided by 0.631. 3.5548, blah, blah, blah. So we'll just call that 3.55 degrees. Now, this is great. So now we have a way to verify if this is correct using this. And we have a way of verifying if this is correct using this. So we can confirm all of our answers with this right here, right? So first of all, we got to figure out what the t total is. It's a real easy way to do that. We just take, because we have this t times the cosine of theta equals this 0.631, we can just say that t tot equals tx divided by cosine theta. So here's the fun part. So tx is our 0.631. Or divide that by cosine of 3.55. Now, this is a 0.632, but you see it gave us an extra little bump on how much is there. And now we have to see this total tension is significant. But before we do that, let's go ahead and check that using what we know about tension in the y. So we're going to multiply this times the sine 3.55, and it's not going to be exact because we're not using an exact figure for our theta, but it should be very close to 0.0392. Notice it's 10 to the third, so we move that down. 0.039.146. Very close. That means that this is all fairly accurate. Now, friction force is equal to this constant mu times the normal force, right? Now, normal force is what stops your tube from accelerating. So when we're stopping it, you're going to consider your center of rotation as this tube, right? That tube has to be stationary, which means that the net forces on it have to be 0. Sorry, I'm starting to get a little off on my talk, but it means that in order for this to be in equilibrium, that normal force has to be equal to the tension. We multiply by this coefficient of friction, which I looked it up, 0.5. That's our total friction force, right? It's going to be essentially half of our total tension. There's no other way that this can be in equilibrium for our starting conditions. If the center of rotation is moving, then we can't even begin to do any of these calculations because we don't have anything that's measurable. So that is why N equals T total. Multiply that coefficient and we get a number 1/2 of the total tension, which was the 0.632, right? So we get 0.316. And that's newtons, right? And like I said, 2.2 newtons is about a pound. So if this is about 1/4 pound, right? This would be about 1/8 of a pound. And that little squiggly marks just means approximately. So the reason why this is significant is because force equals mass times acceleration. That's how force is defined. The mass is being accelerated a certain amount. Acceleration is the change. I'm gonna use this in A with the respect to the change of time. It's a change in velocity. So I'm gonna write it write it in its form. A equals the change in velocity over time. The reason why the friction is significant is because it represents an opposition to the motion. If the force is this high on a mass equals 0.004 grams, let's calculate the acceleration. This is going to be a negative acceleration. So we're going to divide that by negative 0.316 newtons, and this is going to give us something in units of meters per second squared. So let's take a look. Mass, because remember, we're looking for that. So we got, oh, I got it backwards again. Look at this. So we got to do the negative 0.316 divided by 0.004, because it's newtons divided by kilograms equals meters per second squared. So let's take a look. Clear that all off. So again, negative 0.316 divided by 0.004 gives us 79 meters per second squared. Negative. So every second, this ball that is traveling at approximately 6.28 meters per second is going to try to slow down by 79 meters per second. So as you can see, once you stop swinging it, this ball is going to stop rather quickly. And what you'll notice is that the instant you let go, the ball drops down to here, right? As soon as you stop swinging it, the ball drops down. It's going slower. Then the ball will start wrapping around like this, right? And as it's wrapping around, it'll pick up a little speed as it gets shorter, but it's gonna go longer down, and it's just gonna stop, right? When it starts wrapping around this, that is when the kinetic friction has changed from kinetic friction to static friction. So when it becomes static friction, that force of friction is much higher. So high that the thing can't even move anymore. It stops. And that's why it starts wrapping around, because it stopped moving at this point. And the ball keeps moving because it's got to maintain its momentum. So it keeps going around, but as its radius goes down, it builds up a little bit more speed. That's why you'll notice that the coils will start going closer together the shorter it goes, because it's going faster. So it's not having the ability to fall as much. I mean, when you first start, that drops a bunch. Then it starts wrapping around because the tension wasn't strong enough. The tension in the X direction wasn't strong enough to overpower that friction force. So it started wrapping around. I'll guarantee you, anybody who does this, don't pull the string to lower the radius. Just watch it. And you'll see you do not have a system that has any sort of equilibrium in it. If that's not all, please feel free to comment below, and I'll answer any questions you may have.